So welcome to the video lecture series on Introduction to Computer Networks. This is part 2 of our topic on the Internet Protocol. So before you proceed to part 2, I hope that you have reviewed the number conversion, specifically from decimal to binary and binary to decimal, and for particularly 8-bit binary numbers. All right, so IP addresses are the core functionality of the IP protocol. So an IP address is a unique logical address for a given network interface for a host which is in a given network. So an IP address is expressed with a 32-bit identifier. And what it does is that it incorporates two parts into this 32-bit long address. The first part is what we call the network prefix or the network ID. And the second part is the host number. So we will look at the breakdown of this shortly, but let's try to break it down a bit more, how it's expressed. So first of all, IP addresses are expressed in what we call a dotted decimal notation. So this means that for the 32 bits, every 8-bit we encode it into a decimal representation and separate the next 8 bits with a dot. So that is why we call it a dotted decimal notation. And given that there are 32 bits and we are breaking it down into 8 bits, we call this an octet. So there are 4 octets in an IP address. Each octet is expressed with 8 bits in binary, and then we convert the binary into decimal and then write it out as an octet in the dotted decimal notation for IP addresses. So for this particular example, the first octet is 100000000. This translates or converts to 128 in decimal. So the first octet is 128. The second octet has a binary value 10001111, and if you convert it into decimal, this converts to 143. So this goes for the second octet. The third and the fourth are converted accordingly into decimal values and put together into the IP address. So this whole thing together with the 4 octets broken down into 8 bits for each octet and separated by dots is called the dotted decimal notation for IP addresses. So in IP, there's a concept that we call classful IP addressing. And this means that based on the settings of each IP address, the bit settings for each IP address, we can classify or separate the IP addresses into different ranges, and each of these ranges are called classes. So remember, we said that an IP address has 2 parts, a network part and a host part. So for class A addresses, we say that the network ID is of length 1 byte. So that means only the first octet belongs to the network part, the network ID part, and the remaining 3 octets belong to the host ID part. The second class, that is class B, has 2 of its octets. That means 16 bits going into the network ID part, and the remaining 2 octets, that is another 16 bits, into the host ID part. Then class C has the network ID to be 3 octets, that is 24 bits, and the remaining 1 octet, that is 8 bits, into the host ID. So these are the 3 common classes that we commonly use for host addresses. However, there are 2 special classes, that is class D and class E, and they are referred to as multicast address for class E, and class E is a special class of reserved addresses, and we will look at what these mean in details a little shortly. So going forward, there is another breakdown in how we can identify, just looking at an IP address, that which class this belongs to. So for class A, what happens is that in the first 8 bits, we know that this belongs to the network ID. However, if we are just given a simple plain IP address, we don't know how long the network address is, just looking at the IP address. To make that differentiation, we say that in this 8 bits of the network ID, the first bit is always fixed to 0. For class B, we know that the network ID is of length 16 bits, that is 2 bytes. However, when we are given just a plain and simple IP address, what we do is that we convert it into the binary representation, and then if we see that the first 2 bits in the first octet, if it is set to 1 and 0, that means that we have to consider a total of 16 bits as the network ID. For class C, if you're given an IP address and we convert it into the binary representation, and we see that the first 3 bits of the first octet, if it is fixed to 110, we then know that we have to consider the whole 3 octets for the network ID, and this IP address belongs to a class C IP address. For classes D and E, the preset bits or the fixed bits are 1, 1, 1, and 0 in the first 4 bits, and for class E it's 1, 1, 1, 1 for the first bit. So these are reserved addresses and multicast addresses, not commonly used for host addresses. However, classes A, B, and C are commonly used for host addresses, and that is what we commonly see assigned to our machines. And whenever we're given an IP, we just need to convert the first octet into binary, and if we see that if it is set to 0 in the first bit, it belongs to a class A. If the first 2 bits are 1 and 0, it belongs to class B. And then if the first 3 bits is set to 110, the IP address belongs to class C. And the eventual inference is that if it belongs to class A, we have to consider the first octet as the net ID. If it is a class B, then the first 2 octets belongs to the net ID, and if it is a class C, then the first 3 octets belong to the net ID. So a network address implies an identifier for a given network. So what it displays is a group of hosts which belong to a single network. And when we have a given IP address, we say that the lowest number in the network address space is the network address. So how do we identify the network address from an IP address? The method is that you have to leave all the bits in the network ID section intact, and then for all the bits in the host ID section, you set to 0. So it's pretty straightforward if you just compare to the previous slide. So if you're given an IP address and we convert the first octet into binary and we see that the first 2 bits are 1 and 0, we now know that this is a class B address, and therefore we leave the first 16 bits intact and we set zeros to all the 16 host ID bits. So for class A, the second, third, and fourth octets are all set to zeros. For class B, the third and fourth octets are all set to zeros. And for class C, only the fourth octet is set to all zeros. So that is how we can identify which network an IP address belongs by following this method and by identifying the network address. There's another address which is closely related, is something that we call the broadcast address. So the concept of a broadcast address is that this particular address can be used by any host in a network to reach all the devices in that specific network. And the particular address is basically the highest number in that network address space. So that means that we have to look at the range of IPs that is allowed in a given network, and the maximum number that we can reach in that space will be identified as the network broadcast address. So the way that we do it is to leave all the bits in the network ID section intact, and then set all the bits in the host ID section to 1s. So if we just look back, let's say if we have a class C address, we can identify this by looking at an IP address, converting the first octet into binary, and if it is set to the first 3 bits to be 110, we know that this is class C. And for class C, we know that the net ID is of length 3 octets. So we leave this part intact, and for the 8 bits remaining for the host ID, we set it to all 1s. And we convert it into the equivalent decimal, which is going to be 255 for the host ID. The remaining net ID remains the same, and that would give us our broadcast address. So now, let's try to understand an additional addressing component that we call the mask. So a mask could be applicable for a network or a division of a network that we call a subnetwork. So network and subnetworks both can have something that we call a mask, and a mask is used to identify the network or the subnetwork ID from a given host IP address. So this is just another way that we can extract the network address from a given IP address. So instead of converting everything and looking at the different classes, we can use this to identify the network address, and when we know the network address, we can then go ahead and find ourselves the broadcast address as well. And the idea is that we have to perform a bitwise AND operation of the host IP address and the subnet mask. So how do we identify a network mask, or how do we express a network mask? The idea is that for all the bits in the network ID section, you set it to all ones, and for all the bits in the host ID section, you set to all zeros. So let's look at an example here. So we have an IP address of a host as 10.0.0.1. And if we convert it into the equivalent binary, we see that the first octet, that is 10, the first octet 10 converts to 00001010. And that means that our first bit in the IP address is a 0. So that means this is a class A address. So for this, we know that for class A addresses, only the first octet is the net ID, and the remaining octets are host ID. So we take the part for the net ID and we set it to all ones. And for all the bits in the host ID, we set it to all zeros. So now if we perform an AND operation of all the bits of the host IP address and the net mask, you will see that we will obtain the network IP address. So 10, so starting from the right, 10 is 0, then 00 is 0, 000, so everything with zeros will become zeros here, and the ones which have 1 and 1 will remain 1. And if we convert it, it will come to 10.0.0.0. And this is our network IP address.